Modern artificial intelligence is completely dominated by Python-based large language models. By processing massive amounts of text, these systems have mastered human language, flooding our screens with fluid, highly articulate responses to almost any prompt. This probability tree shows how fluency is generated through statistical guessing. It calculates the most likely next word, predicting instead of thinking. Operating on likelihoods, the system inevitably hallucinates, eventually hitting a point where a statistically probable sequence fabricates a factually incorrect statement. Developers call this the black box problem. An advanced language model relies on billions of interconnected parameters. When the machine spits out a false legal citation or a made-up historical event, engineers cannot look inside the system to trace exactly why that specific mistake was made. The sheer volume of statistical math obscures the path. Linguistic eloquence easily mimics human intelligence. But mistaking a machine's probabilistic guessing for actual logical reasoning leaves a massive vulnerability at the core of our most advanced technology. That vulnerability becomes an immediate liability when we move these tools into high-stakes environments. In medicine, law, and cybersecurity, an articulate guess is a liability. A single hallucination in a diagnostic chart or a binding legal contract carries severe, real-world consequences. Curious, to solve a critical flaw in the most complex technology of the 21st century, computer scientists are looking backward. They are resurrecting a highly specific programming tool originally built in the 1970s. That tool is SWI-Prolog. Born 50 years ago, it is an older, quieter language built entirely on rigid mathematical logic. It does not guess, and it does not operate on statistics. As the limitations of probability-based AI become obvious, SWI-Prolog is staging a comeback. It offers the exact mechanism that data-hungry language models lack: a verifiable, step-by-step sequence of reasoning. Standard modern AI uses an imperative approach. Engineers feed a computer an ocean of unstructured data, asking the machine to find the patterns necessary to complete tasks on its own. This diagram shows SWI-Prolog's core mechanic, declarative logic. Instead of throwing raw data at the wall, the programmer defines specific rules and facts. By isolating these rigid boundaries, a logical query traces an unbroken line directly through the established rules. This is symbolic reasoning. The system solves queries step by step. If a statement violates a rule established by the programmer, the machine rejects it. There is no guessing based on statistical likelihood. You can think of the two systems like different halves of the human brain. Large language models mimic intuition, extremely fast, heavily reliant on past experiences, and prone to making things up when they don't know the answer. SWI-Prolog mimics human deduction. It is slower, strict, and entirely precise. By forcing the computer to operate on absolute facts rather than statistical probabilities, logic programming delivers the structural certainty required to actually trust the output of an artificial intelligence. To see how this works in practice, consider an AI system deployed in a hospital to assist doctors with diagnosing patients. If a hospital relies on a standard language model to evaluate a patient's symptoms, the doctor receives a diagnosis but cannot verify the steps the machine took to arrive at that conclusion. If the AI suggests a rare disease, the doctor has no way of knowing if the machine used sound medical knowledge or simply hallucinated based on a statistical glitch. A diagnostic system backed by SWI-Prolog removes the mystery. It provides explainable AI. Because the system operates entirely on established logical rules, every single decision it makes is transparent. Looking at this logic tree, we can see exactly how a doctor verifies the results. They can manually trace the logic backward from the final diagnosis, moving down through every individual symptom and medical rule the machine used to make its choice. In a life-or-death scenario, exposing the mechanical why behind a machine's decision carries exactly as much weight as the decision itself. The goal isn't to delete modern neural networks and replace them entirely with SWI-Prolog. The solution lies in combining their individual strengths. This diagram outlines the neurosymbolic shift. The two systems link together. Neural networks serve as the perception layer, filtering massive real-world data into patterns. SWI-Prolog acts as the reasoning layer, filtered data hits logic nodes, where strict rules organize it into an accurate conclusion. This synergy bridges a massive gap in computer science. By marrying vast data processing with strict logical rules, we create a machine capable of mimicking both the intuitive and the deductive hemispheres of human thought. This neuro-symbolic approach clears the path for the safe, reliable deployment of artificial intelligence inside our most critical infrastructure. With a rigid logic layer, security protocols map cyber threats, legal systems parse binding contracts, expert systems encode human expertise, moving beyond linguistic performance into genuine understanding. As artificial intelligence scales to manage larger aspects of society, verifiable accountability serves as the final barrier against catastrophic mechanical errors. We have to know exactly how our tools arrive at their conclusions. The next evolution in artificial intelligence arrives when we combine massive data ingestion with the 50-year-old art of pure reasoning, teaching our most advanced systems how to think as well as how to speak.